The last time the Atlantic Ocean produced 20 named storms in a single season, the year on the calendar was 2023. Go back one step further, to the season people still name-check with a kind of dread, and you land on 2020 and its 30 storms. A year so busy it burned through the entire alphabet and had to reach for Greek letters just to keep counting. Those are the ceilings. Those are the years that flattened neighborhoods along the Gulf, that put every mile of the United States coastline under some kind of tropical warning at once. And right now, in the summer of 2026, one respected forecast team has quietly put its number for this season at exactly that: 20 named storms. The season has already fired its opening flare. In mid-June, a sloppy, disorganized system spun up in the western Gulf of Mexico and earned itself a name: Arthur, the first named storm of 2026. It never became a hurricane. It barely held together. And yet here is the thing that should make you lean in. The professionals who forecast this for a living cannot agree on what comes next. Some of them are telling you this season will land somewhere near normal, maybe a touch below. Others are staring at the same ocean and forecasting a season that reaches toward 20. That is not a small gap. That is the difference between a quiet year and a year you remember. And by the end of this, you'll understand exactly why they disagree, which side is holding the stronger hand, and why the entire argument comes down to one patch of ocean thousands of miles from the Atlantic. If you like understanding these seasons before the headlines catch up to them, the physics under the forecast, not just the forecast, this is the channel that tracks them as they unfold. So consider subscribing and giving this one a like. It genuinely helps these breakdowns reach the people who want the real version. Now, let's start with where things actually stand, because the season is younger than it feels. The Atlantic hurricane season runs by convention from the 1st of June to the 30th of November. Those aren't arbitrary bookends. They historically describe the period in each year when over 97% of Atlantic tropical or subtropical cyclones form. Think of it less as a light switch and more as a door that swings open in June, opens wider through the summer, and stands wide open in the peak weeks of late August through October before easing shut in November. The ocean has to warm up, the atmosphere has to fall into the right shape, and that takes time. So when Arthur formed, it wasn't early in any dramatic sense. According to NOAA, the first named storm of the year typically forms around June 20th, so Arthur was right on time. It arrived a few days ahead of the average, and that's it. There's a temptation every year to read the first storm like tea leaves, to say, look, it's already starting, this is going to be a monster season. That instinct is almost always wrong, and it's worth understanding why. Look at what Arthur actually was. It was a short-lived and disorganized tropical cyclone, the first named storm of the season, whose origins trace back to a tropical wave that combined with the leftovers of an earlier storm just east of the Yucatan Peninsula. Despite initial skepticism from the National Hurricane Center about whether it would even organize, Arthur scraped together 40-mile-per-hour winds and drifted northeast. To put 40 miles an hour in perspective, that's the wind that makes it annoying to hold an umbrella. It's a strong gust on a highway. It is not, by any stretch, a powerful storm. By late Wednesday night, its top winds had actually fallen to 35 miles an hour, below the threshold to even be called a named tropical storm anymore. But for the purpose of the forecast, Arthur tells you almost nothing. A single early named storm is a data point, not a trend. It's like judging a marathon by who's leading after the first 100 meters. The runner out front might be a contender, or might be someone who sprinted the opening and will fade by mile 2. You can't know from the start. What forecasters actually watch isn't whether the first storm shows up on time. It's the shape of the ocean and the atmosphere that will decide whether storm number 2 and 8 and 15 ever get the chance to form. They're not watching this one small storm. They're watching the slope of the entire setup behind it. And that setup is exactly where the experts start to split. Which brings us to the disagreement itself, laid out side by side, because it is genuinely striking how far apart these numbers sit. Let's establish the baseline first, so every number after it has something to lean against. An average Atlantic season, using the modern 30-year climate record, runs about 14 named storms, 7 hurricanes, and 3 major hurricanes. Hold those 3 numbers in your head, 14, 7, 3, because that's normal. And every forecast is really a bet about how far above or below normal this year lands. Now the official US government position. NOAA's forecasters are predicting a below normal season for the Atlantic, with a 55% chance the season comes in below normal, a 35% chance it's near normal, and only a 10% chance it runs above normal. In actual counts, the agency is forecasting 8 to 14 named storms, of which 3 to 6 become hurricanes, including 1 to 3 major hurricanes. Read the bottom of that range and you get a genuinely sleepy season. Read the top and you're merely at average. Either way, NOAA is telling you, don't expect a monster. Colorado State University, the team that essentially invented modern seasonal hurricane forecasting, lands in the same neighborhood. In its June update, CSU trimmed its forecast to 11 named storms, 5 hurricanes, and just 2 major hurricanes, citing the high chance of a moderate to strong El Niño developing by September, along with cooler-than-expected Atlantic Ocean temperatures observed in May. Notice they didn't just publish a number. They lowered it, and they told you why. That direction of travel matters. The trend in a forecaster's own thinking is often more revealing than the single number they land on. 2 other established groups sit right there with them. In its April forecast, TSR, a group called Tropical Storm Risk, called for 12 named storms, 5 hurricanes, and just 1 major hurricane. AccuWeather, forecasting privately, put its range at 11 to 16 named storms, 4 to 7 hurricanes, and 2 to 4 major hurricanes. That's a whole cluster of serious forecasters all pointing the same direction. Near normal, leaning quiet. And then there's the outlier. On the 7th of April, the University of Arizona posted a forecast calling for an active season. 20 named storms, 9 hurricanes, 4 major hurricanes, and a very high energy index of 155 units. 20! Against NOAA's ceiling of 14 and CSU's 11. That is not a rounding error or a difference in style. That is one group looking at the coming season and seeing something close to 2023, while nearly everyone else sees a below-average year. When you stack the whole field together, the spread is remarkable. Taken as a group, the serious teams huddle between 11 and 14 named storms, with the University of Arizona's 20 sitting far out beyond the rest. So how can serious scientists, all trained in the same physics, all looking at the same planet, arrive at numbers that far apart? It's tempting to think one of them is just wrong or reckless or chasing attention. That's not what's happening. What's happening is that they're weighting one specific ingredient differently, the single most important variable in the entire seasonal forecast, and that one disagreement cascades into everything else. It's the reason NOAA says below normal and Arizona says 20. And once you see what that variable is, and why it's so hard to pin down this far out, the whole disagreement stops looking like chaos and starts looking like a very honest fight over one number in one faraway ocean. To understand that fight, you first have to understand something that sounds almost impossible on its face. How anyone can forecast a whole season of storms months before a single one of those storms exists. The trick is that you're not forecasting storms at all. You're forecasting the room they'll be born into. Think about the difference this way. When a hurricane specialist tracks a single storm, they're watching a specific physical thing, a knot of thunderstorms with a center, spinning over a particular patch of water, moving in a particular direction. They can measure its winds, watch its pressure, feed its structure into models, and tell you where it'll be in 3 days with real confidence. But push that same forecast out past about a week, and it falls apart. Not because the science is bad, because the atmosphere is chaotic in the strict mathematical sense. Tiny differences in today's measurements grow into enormous differences a week later. This is the reason your phone's weather app is usually right about tomorrow and basically guessing about the day 10 days out. A single storm is a single roll of a very sensitive die. A seasonal forecast is a completely different kind of question, and it's worth slowing down on why. Nobody at NOAA or Colorado State is claiming to know that a hurricane will form off the coast of Africa on the 12th of September. That's impossible, and they'd be the first to tell you so. What they're doing instead is reading the conditions, the temperature of the ocean, the behavior of the upper winds, the state of the Pacific, and asking a probability question. Given a room shaped like this, how many storms tend to come out of it? It's the difference between predicting the outcome of one coin flip, which you can't do, and predicting that 1,000 flips will land near 500 heads, which you can do with real confidence. You can't forecast the individual event. You can absolutely forecast the odds across a whole season. So picture two very different jobs. The hurricane specialist is a firefighter watching one blaze, tracking exactly where it's spreading right now. The seasonal forecaster is more like an engineer walking a factory floor months before production starts, checking whether the raw materials are stocked and whether the machinery is running clean. The engineer can't tell you which specific units will roll off the line on which specific day, but they can walk the floor, look at the inventory and the equipment, and tell you with real authority whether this is going to be a heavy production year or a slow one. Counting storms is nothing like tracking a storm, and the whole game of the seasonal forecast is reading the factory floor. So let's walk that floor, because for all the complexity of the atmosphere, the machine that builds an active hurricane season really comes down to 2 ingredients, and almost everything else is a footnote to these 2. The first is fuel, and the fuel is warm ocean water. A hurricane is, at its core, a heat engine. It works by pulling warm, moist air up off the sea surface, where that moisture condenses high in the storm and releases enormous amounts of heat, which drives the whole spinning circulation. The warmer the water, and the deeper that warmth runs, the more fuel is available, and the harder the engine can run. There's a rough threshold that gets thrown around. The ocean generally needs to be around 80 degrees Fahrenheit, about 26.5 degrees Celsius, down through a good depth of the upper ocean before it can really sustain a hurricane. Below that, the engine sputters. Above it, and especially well above it, the engine has room to roar. There's a specific stretch of the Atlantic that matters most here, and it has a name: the Main Development Region. Picture a long corridor of tropical ocean running from the west coast of Africa across to the Caribbean, roughly between 10 and 20 degrees north latitude. This is the nursery. It's where the tropical waves that peel off Africa every few days find warm water and room to grow. And it's the birthplace of the biggest, most dangerous Cape Verde hurricanes, the long-track monsters that get days over open water to intensify before they ever reach land. When forecasters want to know if a season will be busy, the temperature of this corridor is one of the first places they look. And here's the wrinkle that's shaping 2026. For the last couple of years, That corridor was running astonishingly warm. Record or near record warm. Part of why the recent seasons have been so active. But heading into this season, that warmth has eased. Colorado State specifically flagged cooler than expected Atlantic Ocean temperatures observed in May as a reason it trimmed its forecast. The fuel tank is still full enough to run the machine. This is the tropical Atlantic. It's never truly cold. But it's not the overflowing, gasoline-soaked tank of the last few years. Take some fuel out of the tank, and all else equal, you get fewer and weaker storms. That's one hand on the scale, pushing the forecasts down. Now the second ingredient, and this is the one that decides the whole argument. It's not about fuel. It's about interference. And the technical name for it is wind shear. Wind shear is simply the change in wind speed and direction as you go up through the atmosphere. Imagine a storm as a tall, spinning tower of clouds, reaching from the warm ocean surface all the way up to the top of the troposphere, maybe 8 or 9 miles high. For that tower to grow strong, it needs to stand up straight, so the heat engine at the bottom stays lined up with the exhaust at the top. Now imagine the winds down low are blowing one way, but the winds high up are ripping across in a different direction, much faster. Those upper winds physically peel the top of the storm off its base. They tilt the tower, smear its structure sideways, and dry it out. The engine and the chimney get knocked out of alignment, and the whole thing struggles to organize. That's shear. Low shear is a calm, still workshop where a storm can build itself carefully, piece by piece. High shear is trying to build that same tower in a gale, with someone constantly shoving the top of it. Fuel decides how strong a storm can get. Shear decides whether it gets to build at all. So the two questions that govern the entire season are, how much fuel is in the tank, and how calm is the workshop? And it turns out that the calmness of that Atlantic workshop is controlled, to a startling degree, by an ocean on the other side of the planet. This is the part that feels almost unbelievable the first time you really sit with it. The single biggest lever on the Atlantic hurricane season is not in the Atlantic at all. It's a band of water along the equator in the Pacific Ocean, thousands of miles away. And its temperature swings back and forth every few years in a cycle called El Niño and La Niña. This is the Pacific switch, and it reaches clear across an entire hemisphere to shove the Atlantic around. Here's the mechanism, step by step, because it's genuinely elegant once you see it. When that equatorial Pacific warms up, that's El Niño, it triggers a monstrous amount of thunderstorm activity over the central and eastern Pacific. All that rising air has to come back down somewhere, and part of it comes down over the Atlantic and Caribbean. That sinking, spreading air changes the whole pattern of upper-level winds flowing across the tropical Atlantic. It cranks them up. In other words, an El Niño in the Pacific reaches over and floods the Atlantic workshop with wind shear. It knocks the towers down before they can stand. This is why El Niño years tend to be quiet hurricane years in the Atlantic, even when the water there is warm. You can have a full tank of fuel and still get few storms, because the workshop is a wind tunnel. La Niña does the exact opposite. When that Pacific band turns cold, the whole circulation flips. The Atlantic's upper winds relax and calm. The shear drops away. Suddenly, the workshop is still. The towers can stand up straight, and every bit of that ocean fuel gets used. This is why the most brutal Atlantic seasons, the 2020s and the 2023s of the record, so often coincide with La Niña, or with the Pacific sitting in a cool, neutral state. Same ocean, same Africa spinning off the same waves. The difference is whether a faraway Pacific is holding the door open or slamming it shut. Which is exactly why the direction of that Pacific switch for 2026 is the number the entire disagreement hangs on. And right now, the switch is in an awkward, in-between place. Through the spring, the tropical Pacific has been sitting in a neutral state, neither warm El Niño nor cold La Niña, right in the middle. The official US forecasters have been leaning toward that neutral state persisting through the heart of the season, though not everyone reads the coming months the same way. Colorado State, remember, specifically cited the high chance of a moderate to strong El Niño developing by September as a reason to trim its numbers. If they're right, and a genuine El Niño spins up in time for the peak, the Atlantic workshop fills with shear and the below-normal forecasts win. If instead the Pacific stays neutral or slides cool, that shear never arrives, the full fuel tank gets used, and the door to a much busier season stands open. And that is the crack the whole forecast splits along. Every team is looking at the same ambiguous Pacific and betting on which way it tips. The below-normal camp is betting the shear shows up. The outlier is betting it doesn't. Neither of them can measure a switch that hasn't been flipped yet, and that single, unmeasurable uncertainty is precisely why the same ocean can produce a forecast of 11 and a forecast of 20 in the very same spring. And because that switch stays hidden for months, forecasters live with a specific kind of fear. The fear of the season that laughs at the forecast. Because it has happened, and not in the distant past. Start with 1992. That spring, the outlook was for a quiet Atlantic, a below-normal season. Exactly the kind of forecast that lets a coastline exhale. And the season did stay quiet, by the numbers. Only 7 storms formed all year. But one of them was named Andrew. Andrew exploded into a Category 5 hurricane and drove into South Florida in late August with sustained winds around 165 miles an hour, obliterating whole neighborhoods around Homestead and becoming, at the time, the costliest hurricane in U.S. history. A below-normal season by every counting method you'd use, and it produced one of the most devastating hurricanes the country had ever seen. That's the lesson 1992 burned into every forecaster's mind. The season total and the season's damage are 2 completely different numbers. A quiet year needs only 1 storm to find you. Now flip it around to 2013. That spring, the forecasts were loud. NOAA called for an active to extremely active season, 13 to 20 named storms, up to 11 hurricanes. Colorado State was calling for a busy year too. Every ingredient looked right. The warnings went out, coastlines braced, and then almost nothing happened. The season produced just 2 hurricanes, and neither reached major strength. It became one of the least active seasons in decades, a year the forecast community still studies to understand what went wrong. The atmosphere had quietly filled with dry, sinking air, and just enough disruption to smother storm after storm, in ways the spring models never saw coming. Picture a whole field of forecasters standing at the door all season, braced for a crowd that never arrived. That's 2013. It's the humbling bookend to 1992, proof the science can miss high just as badly as it can miss low. And then there's the season that redraws the ceiling, 2020. Pre-season outlooks called for an active year, but nobody's numbers were high enough. The Atlantic produced 30 named storms, so many that the naming list ran out, and forecasters reached into the Greek alphabet. A record 12 of them made landfall on the continental United States. Louisiana alone was struck 5 times. Picture a single stretch of coast getting hit, patched up, and hit again before the tarps were even off the last roof. 2020 is the reminder that the top end of what's possible is higher and meaner than the forecasts usually dare to print. And it's exactly the shadow the University of Arizona's forecast of 20 is standing in. Hold those 3 seasons together because they draw the honest boundaries of this science. 1992, quiet count, catastrophic storm. 2013, loud forecast, empty ocean. 2020, worse than anyone predicted. This is the real range of outcomes hiding inside a single spring forecast. And it's why the responsible move is never to treat any seasonal number as a promise. That uncertainty is honest, and it's published in the open, which is exactly why it's worth pausing on the ideas that circulate online every hurricane season. The ones that say these storms are being made, steered, seeded, or covered up. The people asking usually aren't foolish. They're looking at something enormous and destructive and reaching for an explanation that puts a hand on the wheel. So let me answer it straight, through the physics. Take the claim that a hurricane can be created or steered by some human installation. To even begin to grasp why that's not possible, you have to sit with the energy involved. A single mature hurricane, just in the process of forming its clouds and rain, releases heat energy at a rate estimated at around 200 trillion watts, several hundred times the entire electrical generating capacity of the whole human race, running continuously. That's not the storm's total power. That's one part of it, every second it exists. No antenna array, no ship, no secret facility comes within a millionth of that budget. Trying to steer a hurricane with any human device is like trying to change the course of a freight train by breathing on it. The train doesn't notice. The energy scales simply don't touch. Yes, cloud seeding is a real technology, but understand what it actually does. It can nudge an already primed cloud to drop some of the moisture it was going to drop anyway. It's a gentle push on a system that was already leaning. It cannot conjure a heat engine the size of an ocean basin, and there is no serious science suggesting otherwise. The scale is the whole answer. And the "they're hiding the real numbers" claim collapses under the simplest test. Everything I've told you today came from published sources. NOAA prints its full seasonal outlook with probabilities and ranges on its public website. Colorado State posts its forecasts and revises them out loud, telling you when and why it changed its mind. The University of Arizona's outlier forecast of 2040, the scary one, is public too. That's the opposite of a cover-up. The whole point of a forecast is that it's shouted from the rooftops so people can prepare. When you can read the worst-case model run yourself on a government page, nobody is burying it. So set the noise aside and watch the real signals instead. Because between now and the September peak, the ocean and atmosphere will tell you which forecast is winning, if you know where to look. The first thing to watch is that Pacific switch. Forecasters track it with a set of ocean temperature readings along the equator, and the number that gets the most attention covers a stretch called the Niño 3.4 region. When that reading climbs toward 0.5 degrees Celsius above normal and stays there, El Niño is arriving, and the shear that quiets the Atlantic is on its way, that favors the below-normal camp. If instead it hovers around 0 or slides negative into La Niña territory, the door stays open. NOAA updates its official El Niño outlook around the middle of every month. Circle those updates. They are, functionally, the scoreboard for this entire disagreement. Second, watch the temperature of that main development region, the African to Caribbean corridor. If it warms back toward the record levels of recent years through July and August, the fuel tank refills and the ceiling rises. If it stays cooler, as it ran in May, the quieter forecast holds. Third, watch the wind shear itself over the Caribbean and tropical Atlantic as the peak approaches. Persistent high shear through August is the single clearest sign the season will underperform its fuel. And fourth, watch the forecasters themselves. The mid-August updates from NOAA and Colorado State. By then, the Pacific and the Atlantic have shown more of their hand. The models converge, and the spread between the outlooks usually narrows sharply. When those August numbers move, that's the signal that the fog is finally lifting. Here's the honest bottom line, and it comes in two halves because you deserve both. The first half. The consensus this year genuinely leans quiet. Most of the serious teams see a near normal or below normal count, built on a possibly developing El Niño and an Atlantic that isn't as overheated as it was. That's real, and it's the responsible baseline. The second half is the one that matters more, and 1992 carved it in stone. A low seasonal count has never once been a promise of safety. Andrew arrived in a below-normal year. The season total tells you how many storms form over an entire ocean across 6 months. It tells you nothing about whether the one storm that finds your coast is a nuisance or a catastrophe. A quiet season with your name on it is not a quiet season. Think back to Arthur, the small, sloppy 40-mile-an-hour storm that never became a hurricane, that everyone was ready to dismiss. It still dropped feet of rain, still ran up over $100 million in damage, still cost 4 lives. That was the season's throat clearing, and it already carried the whole lesson. The strength of a storm on paper and the harm it does on the ground are two different measurements, and only one of them shows up in the forecast count. We are better at reading this ocean than we have ever been. The satellites are sharper, the models are finer. The physics is understood in a way it simply wasn't a generation ago. And with all of that, the honest scientists will still tell you they cannot see clearly 3 months into a chaotic atmosphere, that a single hidden Pacific switch can turn their number from 11 into 20, and that the safest posture is to prepare for the high end of what's credible while hoping for the low. The forecast is a reading of the room, not a script for the season. The room this year looks calm, but the door to a loud one is not yet shut, and it won't be until that faraway Pacific finally decides which way to tip. If you want to follow this the honest way, watching the real signals as the peak approaches instead of the headlines and the noise, subscribe and stay with the channel. We'll be tracking that Pacific switch, those ocean temperatures, and the August updates as they land. And I'll walk you through exactly what each one means the moment it moves.